In this video we're going to take a look at the Jeeves challenge on HackTheBox. It's an easy Pwn challenge and the description says, "How are you doing, sir?" So let's start the instance and download the files. We'll try and get this working locally first, so we'll take a copy of the Jeeves file to our local directory and we'll go and do some basic file checks. I will mention that if you're new to binary exploitation, I would advise to go and watch the reg video that was uploaded before this one, where we go through a basic buffer overflow return to win style challenge. I would advise going through that first, although I will make this video in a way that is aimed at beginners and try to cover as many different tools as possible and different options for identifying where the exploit is and how to exploit it. And we'll do that manually, both locally and against the server, and we'll also write a Pwntools script to automate the process for us. So we'll check the file type first of all and see that it's a 64-bit LSB executable for Linux. We can do check sec and see what kind of protections are enabled. So in the last example we had no execute enabled, so we weren't able to execute code on the stack, which was fine because we weren't looking to. All we were looking to do is return to win. So we were looking to overwrite the return address with the address of a function called win or winner or something like that. In this case we still have NX enabled, but we also have pi enabled and full rel-row as well. There's no stack canaries. So let's run strings. I'll do strings-n10 and just get an idea from this what kind of functions are in the program, if there's any useful strings lying around, and we can get an idea what the functionality is as well. So it's going to ask us, it's going to say hi, ask us for a name, and then it's going to, by the looks of it, print the name back to us. And then there's also this, pleased to meet your acquaintance, here's a small gift. We can see some imports and functions, things like that. So we have libc here. So that's fine. Let's do chmod plus x and make this executable. We'll run the program. It asks for a name, so let's put in a name. And it says, "Hello crypto, have a good day." If we try that again and put in a longer name, you see we've got a segmentation fault. So at some point here we overwrote probably the instruction pointer and caused the program to crash. So let's try and run ltrace as well. Ask for the name, crypto. Alright, so we're not really getting any kind of debugging information through that. So one thing we can do is try to open this up in a decompiler. If we open up Ghidra, we can go and compare the assembly code to the decompiled code, so trying to get it back to as close to the C code as possible. Let's create a new project and call it Jeeves, and then we'll import the file Jeeves, and it'll just give us some information about the binary. As you can see here, we can just hit OK, double click on it, and this will open up Ghidra. We'll do the basic analysis checks, just do yes, and we'll hit whatever the defaults are. And here we are in Ghidra. There's a couple of things we could do here. We could go and look at the strings and search for strings, and then you can see our list of strings here. We could click on the strings that we're interested in, like flag.txt for example, and that will take us straight to that point. We can also just go in and have a look at the functions. So we can see the functions here. We can search for either an entry or for the main function. In this case we've got the main right here. Apart from the main, all we really have are the libc functions. So we open up the main function. Another way, as I say, that we could have done that was to look for something like flag.txt, and that would take us to that as well. We can look for references to that, so wherever that takes us to here, you can see here there's the references. We can double click that and it'll take us to the same code. And here we are in our main method, our main function. We have a variable, a buffer that's defined here, 44 bytes. We have some other variables that are placed on the stack, an integer, a pointer, another int. And then we have this local C variable, which is set to a negative big hex number. If we click on that, as we click on these lines, it'll highlight on the assembly code as well what that's actually pointing to. And if we click on the local C, we'll see that it's being assigned this value dead code in hex. And if we wanted to convert this, we can go and convert it, right click, convert, and we can convert it to the various different formats here as well. So, okay, that's cool. We know that local C is being assigned this variable. It asks us for our name, and it puts our name in this 44-byte buffer, and then it prints that back to us. It then checks, does local C, which was assigned this value dead code, does that equal leap babe? Obviously it doesn't. There's no way that it could equal that, because at no point was it assigned the value leap babe, and at no point were we given any option to write to that variable. But assuming that it does for some reason equal leap babe, it's gonna print us a flag. Let's actually just go and quickly create a flag.txt so that we can test this better locally. Let's go in here and we'll say fake flag. Save that. That'll just so I remember to do that before we start debugging. So let me just explain what's going on. So in our last example we had a function called winner, and we wanted to return to that function. In this case we don't have any functions that we want to jump to here, so we're not actually aiming to overwrite the return address, the instruction pointer. What we're aiming to do is overwrite this variable on the stack. So as this 44-byte variable is placed on the stack, we have an integer variable placed on, we have a pointer, so we can go through and calculate what size these are going to be, and at what point on the stack is the local C variable going to be. And there's a couple of ways that we can do this. First of all, if we're in Ghidra, we can actually see how this is being defined on the stack. So we can see that we have this variable that's been placed here. It's at minus 48 here, but we know that it's the 44-byte variable that's being placed there, and there's one of them, as we can see here. We also then have a 4-byte int that's being placed. We have an 8-byte pointer, and we have our 4-byte local C variable. So if we add those together, we have a 44 plus 4 is 48, plus 8 is 56, plus 4 is 60. So that's one way we can determine that. Let's move away from Ghidra and see and have a look at this in some other tools as well. We can open up GDB, PwnDbg, or whatever plugin of your choice, Peda or Jeff, and go through and try and see what this actually looks like in memory as we're going through. So let's do that now. So let's run GDB, PwnDbg, and pass in Jeeves. We open this up. As usual, we can do like info functions. We can see what functions we have here. We know that we don't really have much. We've got a main function, and we don't have, like last time we had that winner function, if you remember. We don't have a winner function to jump to. Note that these addresses haven't been populated either, because we haven't executed the program yet. So we can disassemble. Let's disassemble the main function, have a look what's going on. And this is just the same stuff that we see here on the left in Ghidra anyway. But we know that the important bit is here is the dead code being placed onto the stack. And then at this point down here we have the comparison occurring, where they compare whatever was placed on the stack to leap babe. So by this point we need to make sure that instead of this equaling dead code, it will equal leap babe. So one other thing I'll mention just before we jump into it is let's if you want to look at for commands in here, you can do help. You can then do help files and keep kind of drilling down to get more information here. You can also type PwnDbg, and that'll give a list of all the kind of plugins and programs that you can run from here. So you can run Ropper from here. You can run. We could open up Radar from here and do like our function analysis, and we can go in and do our disassembly here if we want to, and say s main pdf disassemble that. So yeah, just worth mentioning that stuff, and that's fine. Let's set a breakpoint then. Let's disassemble again. Disassemble main. Let's set a breakpoint right. Oh, let's run the program first. We need to run it. And also, actually, let's just do our usual cyclic pattern thing here. Let's do cyclic 100. If you watched the last video, this is what we did to identify the offset of the instruction pointer. So if I now run the program, it asks us for a name. We'll paste in that cyclic pattern, and it's crashed the program, as you would expect it to. And because it's 64-bit, we don't see our string in the RIP, but we can have a look at what's the first 4 values on the stack in the RSP, and we can do the cyclic -L from there. Do cyclic -L, and we'll see that there's 72 bytes. So we would write 72 bytes before we get to overwrite this instruction pointer. The problem is we're not looking to overwrite the instruction pointer this time. Last time we wanted to overwrite this return address with the return address of the win function, but we don't have a win function now. We're looking to overwrite something that's on the stack. So to do that, let's go back again. We need to try and identify the offset. We kind of know it's 60 because we've checked manually through the static code here, but let's disassemble main and let's set a breakpoint at, oh, where is it? Yeah, this compare. So you could do main plus 77, or you can copy this address and do b asterisk for the memory address, paste that in, and that's set a breakpoint for us. Now if we run the program, let me show a couple of things here. So if we run the program, let's just put in crypto, and we'll see that it's braked, it's stopped at the breakpoint, and we can see that the current instruction that's about to be executed is this comparison, where we're comparing what's in RBP-4 to leap-babe. Now if we go here and say x over s RBP-4, oh, that's printed as a string. Let's do x over x. Okay, do x over x there, and we can see that we have this dead code value, which is not leap-babe, so this isn't going to work for us. You'll also see that what we could do potentially here is we could say let's set RBP-4 equals 0x leap-babe. And then if we run this again, you see here cannot access memory address at leap-baf. So the problem there is we have if we go back, actually let me run that again, or let me scroll up a little bit. So you'll see here that what it was actually saying is that was a pointer. So the dead code wasn't actually in RBP-4, it was in the memory location pointed to by RBP4. So instead of setting our RBP4 value, what we should have set is the memory address value here. So if we let's run it again, I'll put in the name crypto, and we'll do the same thing. Let's do x over x RBP-4. We can see that dead code's in there, but it's not in RBP4-4, it's in this memory address. So if we say set this memory address to equal 0x leap-babe, and now we have a look, we'll see that our leap-babe is now in this RBP-4 because RBP-4 is pointing to this address, this memory address where we have actually placed leap-babe. So if I now hit continue to continue the execution, we get pleased to make your acquaintance, here is a small gift, and it gives us our fake flag. So that's all well and good. The issue obviously is that on the server we don't have access to GDB, and we can't go and say, we can't just manually change the addresses in memory. So we're going to need to find the offset of 60, which we already know what it is from this manual, but let's see how we can actually do that using the cyclic pattern as well. So with our breakpoint still in place, let's generate a cyclic pattern of 100 again. Let's copy that. Let's run the program, paste that in. You can see it stops at our breakpoint at our comparison here. And what we want to do is find out actually what is in x over s, because we want to print it as a string, RBP-4, and we'll see that this value is in RBP-4. So what is the offset of this in our cyclic string that we gave it? Let's do cyclic-L to look that up, and we'll see that this is 60 bytes in. So if we write 60 bytes in as our name, the following 4 bytes are what will be placed into the RBP-4, and they're the bytes which are going to be compared to this leap-babe value. So I hope that makes sense. Let's try and test this out manually first of all, just by using Python to print out a payload. Okay, so if we say here Python 2, and it's important we do it in Python 2, there can be some problems doing this in Python 3. Python 2-C for our command line, and then let's say print a times 60, that's our padding right up to the variable we want to overwrite, and then we want to put in our hex values, so we can use \x for each byte that we want to put in. And just as a reminder, we want to put in leet babe, but we want to put it in reverse orders in little endian format, so we can say 13 and then \x 37 \x ba \x b3. Now if we print that, some of these characters don't print properly in ASCII, they're not in the range, so let's print this to a file called payload, and then let's go back to our GDB, and I'm going to delete the breakpoints, and then I'm going to run this with the payload, and you'll see, pleased to make your acquaintance, here's a small gift, fake flag. Let's actually disassemble main. Let's put that breakpoint back in and have a look at what's going on. We'll do B. We'll run that with the payload. We'll see that we've got a breakpoint here, so we can see that we have the stacks filled up with these A's, and we have this comparison that's about to occur. Let's have a look at the RBP minus 4. Let's do x over x, RBP minus 4. We can do x over 8x. You see there we have our values in there. Leet babe, yeah. We can see that we have our values in there. LE, ET, BA, BE. So our values have been correctly written into the right place, and this comparison that's about to occur, if we hit next, so it's going to jump not equal, and depending on our result is where it will go. So if we hit next, well, let's just hit continue there. Yeah, we've got back our flag, and we can just run this as well. We can run Jeeves and just paste and send in the payload, and that gets us the flag as well. So why don't we try this against the server, and then if it works, we'll try and set up a Pwntools script to automate this. So first of all, grab this address, and we can do netcat, paste that in, get rid of this colon, and okay, it actually doesn't. It asks us for the name. It doesn't give us a prompt, so you have to just put in. I'll put in here crypto before it asks, "Hello, sir, may I have your name?" That's fine. Let's run this, but let's send in our payload. So let's do netcat, and then we'll send in payload, and you'll see that it sends that off, and it returns our flag as we expected, which is awesome. So let's go and do some. Let's make a Pwntools script to do this for us. So I'll copy the Pwntools template that I have here, call it jeeves.py. Let's open this up. And a couple of things we'll need to change here. I'm going to get rid of this find EIP because we're not even, although, I mean, we could use it, I suppose, to find the location of our. We could use it to find the 60 bytes offset. Might do that actually. All right, let's give it a go. I'm gonna say it's really not needed, but so we'll say just put in Jeeves here so that can run. It's gonna. We'll do this later. We'll try that out after. Oops. So I'll comment this out. We're not going to bother trying to find the offset first of all. The offset we know is 60, so I'm just going to put in 60 for now. And what do we want to put at the offset? We want to put 0x leet babe. And then we want to write the payload to a file. Well, we don't need to, but just in case we want to save it for later, we want to send it off. Now, the only thing is, it doesn't ask us for. Let's run this locally. Jeeves, it says, may I have your name? So let's say send line after may I have your name, and then we want to receive until, let's run it again with the payload. Here's a small gift. Alright, we'll close that. We don't need to do this. We could just like receive all until we've got what we need. But I need to escape that or change these to double quotes, so I'll just change them to doubles. And then we should get our flag. Let's try this out. So we'll run this then, Python Jeeves. And we can see that it's just freezing there. So let's go and set this to debug, set the context level to debug and try and see what's going on. You can see it's asking, hello, good sir, and then it's not getting any response. So if we go back here, where it's asking, may I have your name? Let's put in, hello, good sir. And let's try it again. And now we get that, it sends that off, it gets the flag, but it's crashed here because it's also then waiting for this flag at the end. So let's we have hello good sir, and then it's crashing here. May I have your name? Pleased to meet your acquaintance. Where do we have this? Let me take away this new line. Run that again. There we go. Alright, turn the debug off, put it back to info. Run that, and there we go, we get our flag straight away. It'll print our payload as well to a file, so we have our payload there. We can see that it's just put in the cyclic pattern right up to the 60 bytes. And if we run Jeeves and send in that payload, that'll work equally well. We can also go and set this to remote instead of debug, and we can go and paste in our server. I have a feeling it might cause some issues because it seems slightly different on the server in terms of it didn't ask you for the name first. Let's see. Oops, not that one. Not that one again. That one. Opening connection. You see that? So that's not actually working for us because it doesn't ask you for the name first. So let's just do their send line. See how that goes. There we go. And we get our flag. So it's slightly different locally, which is fine. Let's go back, set this back to process. I'll upload this script to GitHub. I'd be interested to see if anybody is able to identify the RBP -4 offset here. I did try playing around with it. You need to, if you want to use this EIP, we'll need to just modify it so that you're sending a line after the correct string. So we can go back and say send line after this. I did try going through and setting this to RBP, which is fine. We're able to access the RBP. The problem is accessing the index. If I do RBP -4, it doesn't take us back 4, and I couldn't find a way to find the offset there. So maybe I'll work that out and be able to include it in a future video, or maybe somebody else can work it out and let me know in the comments. That'd be cool. Anyway, I hope you've enjoyed this video, and yeah, any questions, comments, leave them down below. Thanks.